Here's another problem from section 7.8. Here we have an improper integral that is going to require that we use some kind of substitution in order to be able to evaluate it. So we see in parentheses here, there's a lot of distracting things here, but ultimately we see in parentheses this 1 over x. And so we do remember, I say we do, we'll see if we do, that secant squared, I'll say secant squared of t, just to not have too many, not use the same letter. This is tangent of t. So the derivative of tangent is secant squared. So if we have the antiderivative of secant squared, that'll just be tangent. And so when we see secant squared in an integral, we hope that it's something like this, because we don't want to have to do a whole bunch of trig identities and stuff. So I can make it look like secant squared of t, or secant squared of something, by just using a substitution. So if I say, let's let u equal 1 over x, and remember that's x to the minus 1, which we need to know so we can use our derivative rules. So then du is minus 1 times x to the minus 2 dx. And another way of writing x to the minus 2 is 1 over x squared. So du is minus 1 over x squared times dx. Well, in this problem, we have 2 over x squared dx. So if in the substitution here, if I were to multiply on both sides of this equation, the one I have here, if I multiply on both sides of this by negative 2, then I'll have negative 2 times du is equal to positive 2 over x squared dx. And that's exactly what I have in this integration. I have 2 over x squared times dx in this problem. So, so my integral here, the secant squared of 1 over x is going to turn into secant squared of u, and the 2 over x squared and the dx together are going to turn into minus 2 du. And so I'm going to put the minus 2 out here and put the du in here. Notice that my limits of integration need to change because they're in terms of x. And oh, I guess I should have said originally, I forgot I was doing an improper integral. When I'm doing an improper integral, I want to think about running this integral instead of to infinity. I want to run it to some parameter n, and then I want to get an answer, and I want to see what that answer is doing as n goes to infinity. So instead of infinity, I'm going to use the letter n there. All right, so to change my limits of integration, I just go back to my original integration, my original substitution. When x is 4 over pi, then 1 over x is just the reciprocal of that, so it's pi over 4. So here the x is 4 over pi, so the u is pi over 4. And at the top, x is n, which means that u is 1 over n. So now I can evaluate my integral because I know the antiderivative of secant squared is tangent. I know I'm evaluating this between pi over 4 and 1 over n. And so that will be minus 2 times the tangent of 1 over n minus negative 2 times the tangent pi over 4. I remember that the tangent of pi over 4 is 1. And so this is minus 2 times the tangent of 1 over n minus negative 2, so plus 2. To answer the improper integral problem, I need to take the limit as n goes to infinity of this answer. I'm just going to write it this way so I don't have the negative sign in the front. This is a little bit easier to look at. So I need to take the limit as n goes to infinity for this thing. Well, we can do a quick analysis here inside the parentheses. As n goes to infinity, we know that this term is going to 0. We know that the tangent of something going to 0 is going to the tangent of 0, which is 0. And so 2 times 0 is 0. So all of this stuff is getting closer and closer to 0 just by working my way from the inside out. That's basically using properties of continuity of the functions, that if we know where the inside function is going, then that's also that will also work its way through the composition of functions since they're continuous. Anyway, so this goes to 0. So tangent of 0 is 0. 2 times 0 is 0. So ultimately this is just 2. And so this improper integral converges, and it converges to 2.